Hello everyone, welcome to Chemistry by APM. In today's video, we are focusing on electron spin resonance spectroscopy, commonly known ESR spectroscopy. So basic introduction to this ESR spectroscopy. As per the name suggests, this spectroscopy basically deal with this paramagnetic species having an unpaired electron, which basically includes a free radical, transition metal ions, or ions are the molecule having at least one or more than one odd number of electron. That is there should be a no pairing, that is the electron should be unpaired, which gives a paramagnetic nature to the molecule. So here another molecule that carry a angular momentum of a electronic origin, and their identification by using this technique of electron spin resonance spectroscopy. In 1944-45, physicist E.K. Zevsky performed his magnetic resonance experiments in the solids where he observed a strong electronical spin resonance absorption for some magnetic, that is the paramagnetic salt, for very first time. After his observation, this technique was remained as a interesting tool in the case of solid state physics only. The application of the molecular orbital theory after Stevens, that is by Steven, the application of the electron spin resonance spectroscopy in chemistry was the first introduced by the K. Owens, which is the name basically related to the semiconductor chemistry. And the Mercury electron spin resonance spectroscopy is one of the important tools to study the paramagnetic species. It is the branch of absorption spectroscopy in which a radiation frequency belongs to the microwave region of near about 10⁴ to 10⁶ megahertz in absorption by the study of a paramagnetic species to induce transition between magnetic energy levels of electrons having unpaired electron. The splitting of a magnetic energy is achieved by the influence of static magnetic field. So now, basically, the electron spin resonance spectroscopy, also known as electron paramagnetic resonance spectroscopy or electron magnetic resonance, that is the EMR spectroscopy. All three names carry a same meaning and similarly describe the different aspect of a same phenomenon. The electron spin resonance spectroscopy is the another kind of a magnetic resonance, that is the popularly we known NMR, that is the nuclear magnetic resonance spectroscopy. Since both the spectroscopy deals with the interaction of electromagnetic moment of a particle, however, the NMR spectroscopy cannot be for the paramagnetic species. In the both the spectroscopy, the transition of the electron occurs from the one energy level to the another energy level, that is from the ground to excitation. The electron spin resonance spectroscopy is observed in the microwave region. However, the NMR is basically observed in the radio frequency region of electromagnetic spectrum. In comparison to the nuclear magnetic resonance spectroscopy and the electron spin resonance spectroscopy has some limited application since it only deals with the paramagnetic species, primarily the system containing the unpaired electron in organic as well as inorganic molecules, free radicals, and the ionic transition of the transition metal which contain unpaired electron of d and the f electrons. So one of the most important application of electron spin resonance spectroscopy is to detection of an extremely short-lived transition free radical intermediate which are formed in the intermediate stage of a chemical reaction. So the points of difference between these two spectroscopy, that is the ESR electron spin resonance spectroscopy and the nuclear magnetic resonance spectroscopy, points of differences, that is the comparative study is here. The first point is the electromagnetic radiation used in the case of the ESR is belong from the microwave region with the frequency range of 10 raised to 4 to 10 raised to 6 megahertz. While in case of the NMR, the radio frequency waves are used with the frequency range of the 10 to 10 raised to 3 megahertz. However, the second point is here. The electron spin resonance spectroscopy is concerned with the magnetically induced electronical spin state, while the nuclear magnetic resonance spectroscopy involves the splitting of a nuclear spin state. Third point, the electron spin resonance spectroscopy. The radiation frequency is typically held constant and the magnetical field strength is varied, while in case of the NMR, the radiation frequency is varied while the magnetic field strength is kept constant. Fourth point, the electron spin resonance spectroscopy is near about, you can say, 100 times or 1000 times more sensitive as compared to NMR spectroscopy, that is, which is the high frequency of the electromagnetic radiation is used in the electron spin resonance ESR spectroscopy in comparison to the nuclear magnetic resonance spectroscopy. Fifth point, that is the electron spin resonance spectroscopy ESR has short relaxation time in comparison to the NMR spectroscopy. Therefore, ESR is usually performed under a cryogenic condition using the atmosphere of the liquid helium as a coolant to attain a very low temperature, which is near about 10 Kelvin. So here is the comparative charts which shows the comparison of the properties between ESR as well as the NMR spectroscopy. So radiation source in the case of ESR is the microwave, where in case of the NMR is the radio wave. Frequency region for the resonance frequency for ESR is 10 raised to 4 to 10 raised to 6 megahertz, where in case of the NMR it's 10 to 10 raised to 3 megahertz. Next point is the spin under investigation in case of the ESR is the electron spin, in case of the NMR is the nuclear spin. Spin quantum number in case of the ESR S is greater than or equals to 1/2, whereas in case of the NMR its I is greater than or equals to 1/2. Magnetic quantum number for the both these spectroscopies are ML values are ranging from the plus 1/2, plus 1, plus or minus 1, plus or minus 3/2, and so on. The characteristical property that we are measuring in case of the ESR spectroscopy, that is the G value, and in case of the NMR, the chemical shift value, that is indicated by letter delta in the parts per million, that is the delta ppm. Sensitivity of the ESR spectroscopy, so basically the sample requirement is the micromolar concentration is required, where in case of the NMR, it is the millimolar concentration is required. Relaxation time in case of the ESR spectroscopy, that is the relaxation time that is from the coming from excitation state towards the ground state. Is the time for the relaxation, which is the microseconds, and in case of the NMR, it's just a second, so it is quite higher. Then next is the line width, that is the one of the relaxation, one upon a relaxation time. In case of the ESR, it is the megahertz, and in case of the NMR, it's the hertz. Time of resolution in case of the ESR, it is the nanoseconds, and in case of the NMR, it's milliseconds. So this is the comparative chart between the ESR and the NMR spectroscopy. Thank you for your kind attention.